A photocathode is a negatively charged electrode in a light detection device such as a photomultiplier or phototube that is coated with a photosensitive compound. When this is struck by a quantum of light, the absorbed energy causes electron emission due to the photoelectric effect. Uses. For many years the photocathode was the only practical method for converting light to an electron current. As such, it tends to function as a form of electric film, and shared many characteristics of photography. It was therefore the key element in optoelectronic devices, such as TV camera tubes like the orthocon and vidicon, and in image tubes such as intensifiers, converters, and dissectors. Simple phototubes were used for motion detectors and counters. Phototubes have been used for years in movie projectors to read the soundtracks on the edge of movie film. The more recent development of solid-state optical devices such as photodiodes has reduced the use of photocathodes to cases where they still remain superior to semiconductor devices. Construction. Photocathodes operate in a vacuum, so their design parallels vacuum tube technology. Since most cathodes are sensitive to air, the construction of photocathodes typically occurs after the enclosure has been evacuated. In operation, the photocathode requires an electric field with a nearby positive anode to assure electron emission. Photocathodes divide into two broad groups, transmission and reflective. A transmission type is typically a coating upon a glass window where the light strikes one surface and electrons exit from the opposite surface. A reflective type is typically formed on an opaque metal electrode base, where the light enters and the electrons exit from the same side. A variation is the double reflection type, where the metal base is mirror-like, causing light that passed through the photocathode without causing emission to be bounced back for a second try. This mimics the retina on many mammals. The effectiveness of a photocathode is commonly expressed as quantum efficiency, that being the ratio of emitted electrons versus impinging quanta. The efficiency varies with construction as well, as it can be improved with a stronger electric field. Coatings. Although a plain metallic cathode will exhibit photoelectric properties, the specialized coating greatly increases the effect. A photocathode usually consists of alkali metals with very low work functions. The coating releases electrons much more readily than the underlying metal, allowing it to detect the low-energy photons in infrared radiation. The lens transmits the radiation from the object being viewed to a layer of coated glass. The photons strike the metal surface and transfer electrons to its rear side. The freed electrons are then collected to produce the final image. Photocathode materials. AgO-Cs, also called S1. This was the first compound photocathode material, developed in 1929. Sensitivity from 300 nanometers to 1200 nanometers. Since AgO-Cs has a higher dark current than more modern materials, photomultiplier tubes with this photocathode material are nowadays used only in the infrared region with cooling. SBCs has a spectral response from UV to visible and is mainly used in reflection mode photocathodes. B-alkali. Spectral response range similar to the SBC's photocathode, but with higher sensitivity and lower dark current than SBCs. They have sensitivity well matched to the most common scintillator materials and so are frequently used for ionizing radiation measurement in scintillation counters. High-temperature B-alkali or low-noise B-alkali. This material is often used in oil well logging since it can withstand temperatures up to 175 degrees Celsius. At room temperatures, this photocathode operates with very low dark current, making it ideal for use in photon counting applications. Multi-alkali, also called S20. The multi-alkali photocathode has a wide spectral response from the ultraviolet to near-infrared region. It is widely used for broadband spectrophotometers and photon counting applications. The long wavelength response can be extended to 930 nanometers by a special photocathode activation processing. Gauze arsenide. This photocathode material covers a wider spectral response range than multi-alkali, from ultraviolet to 930 nanometers. In gauze, extended sensitivity in the infrared range compared to gauze. Moreover, in the range between 900 nanometers and 1000 nanometers, InGaAs has a much better signal-to-noise ratio than AGO-Cs. With special manufacturing techniques, this photocathode can operate up to 1700 nanometers. Cs-Te, Cs-I. These materials are sensitive to vacuum UV and UV rays but not to visible light and are therefore referred to as solar blind. Cs-Te is insensitive to wavelengths longer than 320 nanometers, and Cs-I to those longer than 200 nanometers.